as always. Now I'll make the recording. The demo I'm going to make to you is a simple optimal buffer allocation. Because of using facts, of course, in real life problem, you have more other decision variable. But buffer is something easy to do. And then it's also interesting there because of, we talk about this integer variable. So many optimization, they have problem to handle buffer, not because of a buffer is necessary a more complex problem, but there are two things that make it complex. One is this integer. Another thing is why the buffer matters is because of the variability. And then if you follow the instruction on 8.2, you will not miss anything. But in this case, I think I will just give you a quick demo so that you will not, or you have the same information when you start this, your lab next week. This is the model I built, and then what the buffer size here, they are not very important because we will later change the value by the optimization. We go to the experiment tab. In here, be careful is when we have the standard setting, by default, it will run the optimization by 6 days. Check your instruction whether this match, but if I'm not wrong, I think all these are based on the same setting by default. But one thing I need to remind you, because over the years, when I supervise students in real lab in computer room, I find some students, they like to continue to click on the shifting bottleneck detection, maybe because of they start with chapter 4 and they find that maybe it's useful to click on the shifting bottleneck. But something is not good here is a shifting bottleneck will cause the system, the simulation, to log a lot of extra data to calculate this active period. And then for running optimization for each individual solutions, it's not that useful to look at shifting bottleneck. And that's why I would recommend you to disable shifting bottleneck whenever you think about running optimization. Otherwise, you will risk that you cause something extra. You know, that there was sometimes in the computer room, two students start the same optimization at the same time, and then one of them find out later why his or her optimization is much slower than his friend or her friend. The reason is usually because of the guy that is more slower, they have the shifting bottleneck detection clicked. So make sure that you disable it. We go to edit optimization. And then of course, now I already have some parameter, some buffer there. I can take them away. So when you start out with, you get nothing here. So if you start with a new model, you don't have any setting. You start with it empty. So let's start with empty. For a optimization problem, of course, you need to have the objective. If you don't have the objective, we talk about that it's not an optimization problem. But of course, you also need to have the variable you need to optimize. So if we click add input variable here, I'm sorry I cannot zoom, but hopefully you still see what I'm doing. If I click in operations, what can I optimize an operation? We can optimize the processing time, but in this case, more specific is the value of the processing time. And then for failure, we have the availability and MTTR that we can optimize. And then whenever I click tip the label here, you will see that there is some number appear on this part. I hope that you see my mouse here. Now I'm on the number on the lower left part. This is the default setting. So the default setting, if you remember, we have 1 minute. Now, let's not bother about the processing time. We go to the buffer. Again, when we go to the buffer, we see there are certain decisions variables that we can change. Again, we can even change the processing time of the buffer if your buffer represents some transportations. But when we click the capacity, now the default option we have set as the number 1 indicate on the figure. You also see number 1 here. So your job is to first delete the default setting if you don't want to have the default setting. Of course, you can also include your default setting, the current setting, into the optimization. Many other software, I don't even know which one actually support that, but FACS support something called a multiple choice set. Multiple choice set means that if now I give you another range, let's say that 4 to 10, and then I add it, you see, now I have a multiple choice. Why I call it multiple choice? The reason is because of I can select from 1 or 4 to 10. So if your intention is to have a multiple range, not a single continuous range, then this will be useful. But in this case, probably this is not something we want. According to the setting, is a 1 to 100. And let's say that if I put 5 here, what happens if I put 5 here? If I really do it in this way, then what you will get is the optimization will test 5, 10, 15, 20, and so on until it reach 100. So if you want to have a step size of 2, then you can do in this way. But if we don't, we want to have a, according to your lab instructions, I think it's 1 to 100. Now, remember to click the green button, the green cross here. But if you don't do that, you cannot press OK either. So we press the green cross so that we add it to the multiple choice set or the range set. And then now we click OK. Now you have the first variable added. And then sometime you can also make the change. If you need, you can make the change here. So it's not necessary that you must here, but I think you cannot change the type. If you change the type, you're going to change the variable. And this is the mixed integer problem here that makes also facts powerful based on this materialistic principle. Now, if we don't want to be so cumbersome in order to add 1 buffer, 2 buffer, we can also add all buffer if you have all the buffer have the same setting. So we chose the option called the add input. Very similar. Now we add 5 buffers at the same time. And of course, you may ask, okay, maybe not all of them will have range 1 to 100. Then you can add all the variable, and then you can come back and do the change here. As I can show you very quickly here, you can do the change here if you want. This is what I want. Well, this is not what I want. And then you need to have the output. So classic factory physics output, throughput, lead time, and work in process. We add them. And then after we complete this input and output, then we can go to the formula. I already make it here, which I make this called the total number buffer. Of course, I make it one change more, but now the name are the same. So you can see that one of the objective is the total number buffer. And this scenario is what we call lean buffer in the PowerPoint slide. And then TNB, okay? If I now do one more time, you will see that how I do it. I just give you a quick demonstration. You can call it whatever you like. You can call it TH or TP or whatever you like, but the formula need to match the variable. And in order not to avoid a typing error, one option you can choose is to drop the output variable if it's a single output variable. So now I put throughput here as the maximize. Now I add another objective, and I like to call this a total number of buffer, or you may call it lean buffer. And then unfortunately, in bottleneck analysis, we have some more automation. But for adding a buffer, sorry that this is a bit stupid, but you need to do it one by one. And it may be time consuming. You will have a 100 buffer, but if you have a 100 buffer, I will recommend that you have a trick there is you open the XML file of your model, and then you can directly add it in your XML file of your model. Now, I stop here. I want to ask you one important question here. If I now proceed to run the optimization, I will get the wrong result. So 95% of the students, when they show me their result and tell me that why their optimization did not converge, then 95% was because of one error. Now I have made that mistake here. What have I made a mistake? I give you like 10 seconds to spot something that is wrong here. I hope that you is large enough, but I give you some time to spot it. I haven't really completed. Yeah, I think good. I think many one of you in the chat, you already answered very correctly. Yes. Remember, this one by default is maximized. Unfortunately, you cannot guess. We should have some more AI there, and then when people see the buffer, then most likely people want to minimize, because if you want to maximize the buffer, then you do not need to optimize it too much, because you just make it maximum. We need to minimize here. So this is very important. 95% of students, 95% of students, if they don't get a Pareto front, it's because of they forget to change this to minimize. We don't have any constraint here, but I can make you one constraint to show you how this concept works. Let's say that all the buffer together need to have a capacity. Oh, I can just copy here. I copy this one in order to save some time. And let's say that I have a constraint here. I want to say the total number buffer will be equal to 200. Now this is a classical buffer reallocation problem. And that means you have already ordered the buffer, you already paid the investment, but you want to shuffle the buffer along the line so that you want to know what will be the optimal changes. And this will be useful. And you know, this equality constraint here, there is a special way in the software to handle this. Actually, if you rely on the genetic algorithm to generate solution randomly. So remember, when we talk about genetic algorithm, we talk about that we talk about the randomization is a key mechanism to generate new solutions. So if you use a randomizations to generate the solution and then hope that they will be feasible, then you end up with a lot of infeasible solution, because the mechanism will keep generating solution, and then, okay, if it's infeasible, then we throw it away and then try to generate another one. And you end up with the software, sometimes even, it does not really crash. I tried the software that are not able to handle the equality constraint. It's not because the software crash. It's just because it end up with some infinite loop, have trouble to find a valid solutions. In this case, I don't want to make this more complicated. I just take it away, and then and then it's actually not make sense if you want to minimize the buffer, but you put the buffer as constraint. But that objective or constraint will make sense if you minimize the work in process or cycle time. Now we choose NSGA2, and there are more advanced variant of NSGA2 which we will cover in another course. That is something we call NSGA3. And then we may also cover some other things later, but for this course, choose NSGA2 by Professor Depp. And then for default setting, if you see this option, if you only have the buffer, you can do one thing that I'm doing here. Uniform range. We talked about this uniform range last time when we talk about genetic parameters. So you may want to tune this into uniform for all of them. But my hint to you is for this simple problem, I don't think you have any trouble if you just choose any of them, because the problem is too easy. So this is not a very complex problem. That's why it doesn't really boost up the performance if you change it. But anyway, I try to change it here. And then in your lab, if you find that you don't see this advanced option, I can tell you a trick here. So now, for those of you who are in this lecture, you can see this is something that I don't have anything good document. I have a quite good desktop, powerful desktop here. So that's why I run 8 cores together. So this maximum parallel iterations is a tricky thing that you can check on your home computer. If you have a good laptop, maybe you can choose 4. But if you have a slow computer, you don't want to be 100% your CPU occupied by the optimization. Maybe you want to choose 2 or even 1. But in my case, I will go, let me just choose 4 because I'm still running the lecture. Let's see what happens. And then I have a show advanced optimization setting, clicking yes in the option. So now if I make it 4 parallel runs, so that means each time when I click the optimization run, it will be, I run it to 5,000, which is something the same as in your instructions. So if everything is correct now, so I start the optimizations. So by the time that the optimization start, the model is too simple. So by the time I'm talking, it's already running, already 60 run. But one thing I need to remind you as well, as a demonstration is here, every point, they are not coming from one simulation. So every single point, they are coming from 10 replications. Why I know that is 10 is because of here, the number is 10. So remember, when you choose this number, call it 5,000 iterations. So the term here is number of iterations. It's not simulation because the total number of simulation you run is 5,000 times 10. And that's why if you have any overhead due to shipping bottleneck data login, then you will have make your optimization run much longer. I think I stop here for the demo. So in case you still have questions, I think either now today you can ask me, or later you can send me email or even ask Matthias. I think both he and me have done this kind of exercise for many students and industrial people for a very long time now. I think more than 10 years we have done this kind of exercise with students. And of course, sometimes we add some new things. And then the bottleneck detections in the last part of my lecture actually was something a bit new. I think that was something we start to launch maybe 3-4 years ago. Now I cannot launch it. I'm sorry about it. So maybe we don't go to the handbook. Aha, I launched it, but it's in another model. I'm sorry. Chapter 10, you need to ask Matthias. I don't know if you need to go through all the way to chapter 10, but if you need to, it's still very simple. And then quite much you can read here, part of them coming from the thesis of Jacob Benedictson, who was one of my students who did the bottleneck analysis. Quite much information was from his thesis. But then there are a very simple model there, which I'm going to talk about now, okay? So let's say that you have a simple problem, but then you have the processing time. Now this model is, this line is very simple. You have the processing time according to here, the seconds, 32, 35, 30, okay. So if just give you the information about the processing time, then maybe you guess by the common sense of cycle time bottleneck in industry they call. So you may say that M2 is the bottleneck. But then if you look at the availability here, then your conclusion may not be very clear because now the higher availability will be better. So in this case, maybe M3 is the bottleneck. But then, okay, what are we talking about? Are we talking about M3 or M2? So which machine is actually the bottleneck? Or maybe you can call them both of them, but if you want to improve one of them first, then will you choose M2 or M3 first? Or maybe you will just decide that you need to improve both, but will that afford, are you afford to do that? That will be questions that relate to what we mean by bottleneck analysis. So this will be something you can read in the chapter 10 of the handbook. And now go back to my PowerPoint. I've done some demo. I think I will skip the significant dominancy in order to spend more time on the bottleneck. So here is also another example, which show you not only about different bottleneck method, but also tell you that different bottleneck mechanisms, definitions will give you a different answer. Now I already give you an answer, but I think in February, when I was a PhD opponent for a PhD student in Chalmers. So his thesis was about bottleneck analysis. And then in the defense process, the first questions I asked him was, so is it possible that you have a different definitions of bottleneck? Then the answer was yes. Okay, so, but then the second question I asked was not easy to answer because of, I asked the question is, if you have different definition of the bottleneck, and it lead to also different method that you find the bottleneck. So will this method give you the same bottleneck? And he thought a little bit about that, but his answer still was yes, which I'm a bit puzzled because when you look at the example I'm going to show, then it will be a different story. Look at the data here. If you spend some focus to look at the data, the transport time of the AGV, they are a little bit deviated, low 1 and 2. This is the classical way, in fact, that you use an assembly to simulate an AGV. So in a future version, hopefully 2022, when we have a 3D effects, then maybe we have more explicit support of AGV. But now bear with us that we have the assembly object. But if you look at the time of the operations, you could find that here, we also have a different processing time, even though exponentially for the MTBF and mean downtime, they look the same, but there are some different processing times here. Now, we want to locate the bottleneck. No matter you talk about the bottleneck of the AGV or in the machine, we want to know where is the bottleneck in order to make the improvement. We go for common sense in industry. There are people, when you ask them where are the bottleneck, the quick answer sometimes will be they pick up a station that have the longest processing time, running time. That is one possibility. But then another not very good answer will be, oh, look at the buffer. When you have the parts accumulate in a buffer in front of a station, then you know that there is the bottleneck. I think this question was asked by my colleague to another PhD student, I think almost 15 years ago. Okay, the answer was look at the queue length. So if you look at the queue length here, so we mainly talk about the queue here. Okay, what will the conclusion you make? Now you see that it seems that here, that means Q1, the buffer before the AGV1 process, then here is the biggest queue. So by looking at the queue length, not directly looking at the AGV, so we have a 1, 2, 3 here. So the first AGV here will be the bottleneck according to the queue length. Now this is one definition. So we check the queue length. And then of course you can ask yourself what happens if you don't have enough buffer or not even have the buffer. So how can you detect it? And this is also very commonly understanding in industry. It's about working and fail time plus together. And sometimes people just call it utilization. But this one is more detailed. It's talking about the workload. It's the working plus the failure. Now, if we look at the calculation here, we find that, of course, for the loading and unloading, we do not count. But if we just count the working, M2 is slightly higher than the AGV3. And now we come to a dynamo now. These workload definitions, which one have the highest workload will be the bottleneck. Tell you that the primary bottleneck is M2, and then the next one is AGV3. So the first one we talk about, AGV1, was not even there. It was the third one, okay? So now you have dynamo. Which one is the primary bottleneck? And then another thing more advanced, he developed the first by a German. That German is now as a professor in Germany in Karlsruhe, but he made this study when he was in Japan with Toyota Software Lab. He published a paper called the Shifting Bottleneck in Winter Simulation Conference. I think it was 2002, the first paper. He talked about a concept called the shifting bottleneck, which you count the active and inactive period. So I think this one needs to be circled because this one is important. You group the working and failure and also set up into something you call active. And then everything else, waiting, blocking, and then the break of the operator, workers, or the uh, um, this is called unplanned. It means that is planned not to have any process. So this is not failure. Failure would be in red, we call failure. But if you plan that in this shift, the machine is not working, that you call unplanned. So everything else here will be called inactive. Now, if you need to calculate this active inactive period, as I mentioned in the demonstration, you need to have a lot of data logging in order to keep all the entity checking when they are active, inactive, active, inactive, when they get in different status. So if you put them according to this, and then we have this free machine scenario, you could see that the chart here show that the solid line here will be the active, and then the dashed line here will means inactive. And this is a one wheel that you can put, but then the calculation will show you if during a period, if a certain machine that has the single surely longest time in the active period, while the other machine can be alternating active and inactive, then you can see that this gray bar here is the sole bottleneck. And the sole bottleneck this period will contribute to the total percent of this gray bar, solid gray bar here, called it the sole bottleneck. I have done something wrong here, and that will be better to tell it will contribute to M3. So you will be here, okay? So this is a comparison between M1 and M3. And then look at another interesting figure here is when you have the shift from one show bottleneck, and then you shift to another show bottleneck, but there is a certain period that they overlap each other. This is what the professor called it the shifting bottleneck. And this part will contribute to the shifting here. Both parts will be calculated. And then even though I think there are people use this method on real machines, but you still need to process the data because of by detecting the shifting, you can't just do it during the simulation run. You need to do it after you collect the data, after you run your simulation or you get the real data, and then you process to know where is the shifting and where is not the shifting. Now, shifting bottleneck is something that I think in Sweden, I think people talk about, we have implementation in facts, and then I think you have research just in Chalmers very actively looking at this method. But I also want to tell you that the shifting bottleneck that you can calculate using this simple model will also be a bit confusing, because now in this case, we see that the place between AGV1 and AGV3, they swapped it. The reason is also because of, if you look at the comparison here, they are actually not very significant difference. The good thing with shifting bottleneck compared with like the utilization, which I always emphasize in my lectures, in terms of utilization about the workload, the contrast is actually not that much. So you don't see there a clear contrast among the bar there. But the shifting bottleneck, one good thing is, apart from its novel definitions, it gives you something different from the workload. It also usually gives you a higher contrast. So in this case, if I need to compare, you can see that the difference between the primary and the second now become more clear. But for shifting bottleneck, you still pick M2, okay, here as the primary bottleneck. So which one shall we believe? So I will introduce to you something we call shifting score, means simulation-based constraint removal. So simulation-based constraint removal. And that was a name termed by Leif Persson in his thesis, published in 2013. And then later on, another thesis by Benedictson, 2018, to follow up this work. Now, the formulation is very interesting. We want to maximize one objective we call performance. And then we just say that the example is throughput. But interestingly, in industry, when they talk about bottleneck, they also mean throughput bottleneck. What do they mean? Where is the place, where is the station that limit, that refrain the throughput performance? That means refrain the system from having higher throughput. And this situation, you hear that very often in the future, and then maybe in your final year project. For some company, they expect their target capacity to be in certain level. But then later, when they run the line for some time, when they start to have more changes and even to certain degradations, or just because of some changes of the product range or the product variant, they find that their capacity is very far from what they have ordered from the beginning. And then the $1 million questions will be how or what should they do in order to come back to the original capacity. So I get this kind of questions very often from company, and sometimes maybe they formulate in different way, but to the end, I think the bottom problem, the bottom line is still the same. They want to improve their throughput. But now the second objective is very interesting, is we do the changes on the parameters. But this will be a binary variable. Why is binary? We have a x, that means the things that you can change. If you keep the original value, we say that it will be 0. So whenever you have the original value, then we will be 0. But then if we have to improve the value, let's assume that the user can decide the improvement to another level, then this will become 1. And that's why I call this I as an integer binary variable. It's not even integer, but then x belongs to the decision that you can make. And then converted to I means that it convert to a binary variable. Now, the optimization will do something interesting. I think this figure will tell you some important informations, but I think the animations may be even more interesting. Let me just run you the animations. Now, this is how the NSGA2, if we formulate the problem into this two objective, on the x-axis, we have the improvement, and then now you may be more customized to what I show usually. We want to minimize the number of changes, and then we want to maximize the throughput. Now the optimization is still running, but then gradually, you will find it is more like a curve, right? And then the curve is what we call the Pareto front. I think now to the end, it will be something maybe similar to this. And then I told you before that we start with the one of the extreme solution. You start with a 0. 0 means that what is your current status of the system? What is the current performance of your system? And then what kind of X we can change? In typical example, you can change availability of the stations. You can change processing time. You can change the repair time. Now, pay certain attention here. When I show the workload, queue length, and shipping bottleneck, mainly I could locate which station is the bottleneck. But now you look at this data here, we are actually working in another level. We are not talking about which station only. We are talking about which parameters of the stations. So these attributes, they connect to operations, but you can also make them connect to buffer, HEV, or something else in your model. But we try to make these variables into the optimization so that to the end, when we make the non-dominant sorting, we are actually sorting about the minimum number of changes in this variable, not about which machine, but on which variable to make the changes in order to achieve the target that we want to achieve. I give you a practical and a very interesting example. And then this is the result coming from SCORE. I will come back. Okay, let me just quickly show this slide. Go back to this slide. When we run the optimizations, we have the improvement, minimization, we have the performance improvement. do we end up with this rank level 1 line here? So they dominate the second rank. So assuming that we afford to make, I don't know, let's say that we afford to make 4 changes. You can see that these 4 changes maybe it's not that much. Let's say that more changes. Let's make 8 changes. So you see that these 8 changes will dominate another 8 changes a little bit here. So that with, oh, sorry. You see that the 8 changes here give you the throughput will be in this level, right? So for another level, you find that you actually, yes, you come up to here, but you actually make more changes because the x-axis has large number. So if you compare this horizontal line here, why we mean this optimal solution dominate, another solutions on the on the dominated solution. The reason is because of the same number of throughput can be achieved with a less number of improvement. And then through something we call frequency analysis, that we pick up all those changes, and then we do a frequency analysis, then we can make a bar, and then to know that which parameter will be the primary variable that we need to change. The result, go back to the AGV example, the result will be like this, so that now you're not seeing anything related to queue length. It's not about the workload. It's the calculation coming from the frequency analysis of how frequent the solutions appear on the Pareto front. And then in this case, we see one M2. Once again, we confirm that machine 2 should be the bottleneck. And now we see that the second one is the AGV3. I don't remember. I think this one is closer to the workload. So once again, I think this one tells us M2, but this time I think we can more or less confirm that M2 is the bottleneck according to this multiple analysis. Jakob Benedictson, he has made certain comparisons. So in terms of applicability, and then in terms of finding where and what to do, I think this is the comparison. So in most of these cases, of course, in his thesis, he will say that the score method based on multi-object optimization is the best in terms of where and what, and the applicability is the highest one. But remember, here is his warning here. Most of the other method, you can just get it by one simulation run. But score method is based on optimization. So it's comparatively much slower than the other method because you need to run multiple runs in order to get the bottleneck. I mentioned about this PSE textbook. So this is the definition I borrow from this Michigan University professor. They define bottleneck in a way very unique. I think so far, I find not many people really stick to their definitions, but this is the most interesting definition. So the bottleneck of a production line is where the infinite small improvement can lead to the largest improvement. So he even can show them in mathematical way. So if you make one changes, and if these changes will dominate all the other changes, like here, so one I that will dominate all the other j, that was what the formula here means. That will be the bottleneck, and then you even can do it for the buffer. So if you have a one buffer I, that if you improve this one, you change this one, it will dominate all the other j buffer, changed in the j buffer, you will get the highest throughput, then this is the bottleneck. So the interesting thing is that you can convert this into the by objective optimization problem. So that's how I maximize the throughput and minimize the improvement change. Now, spend some time to think about it. Can you have another objective instead of throughput? Of course, right? Because of you just need to change the objective here so that you can apply the same principle. So you can apply the same principle to find the optimal changes in order to achieve your target. And that is something quite interesting because of when we go back. to my proactive view here. Earlier in the earlier part of the lecture, we talk about what we can use optimization to help us to find the improvement. So here is the trick. You, based on which objective you want to improve. In this case, we see that this is cycle time. We want to keep the throughput, but we want to reduce the cycle time. So your question is to, or your responsibility is to use the optimization to find where you should make the optimal changes in order to achieve your target with respect to the objective that you are interested. So in the very last part of my lecture, I want to show you one award. This case study, we did it for Volvo cars. We did an award. We got an award, Volvo Car Technology Award. So this was a complex line built by a production engineer in the industry. And then they had the trouble. They want to increase the production line of capacity by 50%, which is huge, 50% of throughput. They expect, or they suspected that the bottleneck was here because that was a more complex transfer line. But when we apply this score method, here you see the result. I can zoom in a little bit so that you can see more clearly. I do not want to show the real value, so that is why the relatively improved on the throughput, 50%. So there were totally 464 possible changes. But out of these 464 possible changes, to the end, the optimization find that there were only 8 changes, sorry, 7, as I show here. The 7 changes of these 7 parameters could lead to the improvement for 50%. And that's why when we, after the optimization, we can locate where they are, and we even have some other data analytics result to show the combinations of the parameters. But anyway, you could find that the primary bottleneck, the secondary 1, 2, 3, 4, they are more in this reagent. So none of them are really from the reagent that the engineers expected. And then we also find that the system saturated after 80% of improvement, but this is not something they're interested to know because nobody really afford to make so many changes in order to achieve that. So their target was to improve by 50%. So I think I stop here. I have 2 minutes to go. I want to know if you have any questions to me. I think I can stop the record.